Okay, section 7.2. It's called the binomial distribution section. We've actually done problems like this way back in chapter 6 at a very, very low level, so we're going to extend that level. So remember the problems in chapter 6 where I said, what's the probability of getting exactly 3 heads in 7 flips? I think maybe on the first midterm there was a question that said something like, what's the probability of getting at least 1 head in 7 flips? That sort of thing. That was an oversimplified version because the probability of heads and the probability of tails were the same, both 1/2, which is why we had that 2 to the 8th in the bottom, or 2 to the 7th, or however many times we're flipping. So it's oversimplified. So we're just going to extend the idea a little bit more in this section. And the question is this: the proportion of adults 25 and older with at least a bachelor's degree is 25%. What's the probability that exactly 3 out of 8 randomly selected adults will have at least a bachelor's degree? So you can see it's very similar to the problem we did flipping a coin. If this were flipping the coin problem, we would have done 8 choose 3 over 2 to the 8th. And the 2 to the 8th is how many outcomes there are, and the 8 choose 3 was how many different ways there are to get 3 heads. But we never really took into account the tails and all that, and that's because the probabilities were the same. So this problem is going to be very similar, but a little bit different. All right, so this is called a binomial distribution. There are some conditions, 4 conditions that must be met to be able to use the formula for binomial distribution. All right, so we have a series of trials that satisfy 4 conditions. The first condition is that it needs to be binomial. Each trial can only succeed or fail. They give a little mnemonic device to help out with this. So they use B for that. The second condition must be that each trial is independent of the other trials. Flipping a coin, independent. The bachelor degree, each person would be independent. So I for independent. And there must be a fixed number of trials to start the problem. We call that N. This seems a little bit weird to have this because, yeah, of course, there's only 8 or 10. But there's another problem coming up in section 7.3 where we don't have a fixed number of trials. We just continue to go until we meet a condition and then we stop. So that's a different distribution. So that's why we have that one. So N for that one. And then S, the probability of success is the same for each trial. So BINS, just to help you remember. I don't know why they picked S. I guess S for the same. I guess because BIMP for probability wouldn't make any sense. I don't know. But these 4 conditions must be met to be able to use a binomial distribution. And now we just need a formula for this. Normally, if we were in a class, I'd probably walk you through this and have you try this a little bit. But I'm just going to give you the formula. The random variable X that counts the number of successes in N trials is called a binomial distribution. And that probability that we get K successes is N choose K times P to the K times 1 minus P to the N minus K. It looks pretty complicated. It's very simple, very simple. And I'll show you how it works. So here's how it works, basically. So we're going to do the same problem, right? So we're going to go probability 3 out of 8. We're going to call these successes, whatever they are. In this case, my probability of success from this problem was 25%, right? So here's the way I look at it. It works similar to the heads, tails problems, but we have 2 different probabilities, right? So we're going to have that 0.25. There's going to be 3 successes. So we're going to multiply that 1/4 in essence, right? So it's 1 out of 4. So this is like 4 to the 3 because there's 3 different ones. So that's the 2 that was in the heads problem. But the 2, the next one was also a 2, right? But in this case, ours is not going to be a 1/4. It's going to be a 3/4 on the next one, right? So then we're going to go 0.75. If we're going to have 3 successes, there must be 5 failures. And a lot of people like to stop it, doesn't it? I got it. But this only tells us 1, 2, 3, 4, 5, 6, 7, 8. It's like this: success, 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 fail, 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 fail. So this number, the 0.23, there's a 0.25, 0.25, 0.25, 0.75, so on, right? But this isn't taking into account all the different ways that we could get this. This is just, if I answered the question this way and just said my answer was 0.25 to the 3rd times 0.75 to the 5th, that would be the answer for getting like 3 successes and then 5 failures. But those can move around, and they move around just like the heads and tails. So at the beginning, that's the choose. We need an 8, choose 3. So I'll go through the whole math here. We're going to go 8, choose 3 times 0.25 to the third times 0.75 to the fifth. And I get not the right answer. So we're going to try that again. 8, 8 choose 3 times 0.25 to the third times 0.75 to the fifth, 0.2076. Pretty straightforward. We might extend the idea and maybe say probability of at least 1 or something like that. So we just think about it the same way we did before, 0, 1, 2, 3, 4, 5, however many. If we want at least 1, it means add up all of these. So we would just take the 0, right, and subtract the answer from 1, just like we did back in the old days. Okay. So the only problem with this is a nice little method for finding exactly 3 out of whatever. But when the number starts to get bigger, this gets to pay. So imagine me saying, like, find the probability of getting at least 10 out of 100. And now you got to add up 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or at least 50. So what we do is we can simplify this a little bit. When we learn a little bit about what happens with these binomial distributions. So it turns out that any binomial distribution that you do, we can figure out the mean and the standard deviation. Again, if this were a regular class, a regular year, this is a regular class, I'd probably spend a little more time. We'd probably do some evaluating in class, but it's not a huge big deal. But it turns out that the mean of every binomial distribution is just n times p. That's how many, or the expected value on average. What do you get? If you're going to flip a coin 50 times, the expected value is 50 times 1/2, or 25, right? For this problem, if I was going to pick 8 people, right, and there's 25% chance, that means the expected value would be 2. If I were to do 8 people over and over and over and over and over and over, sometimes I'm going to get all 8, sometimes I'm going to get none, but on average, I would get 2. And then the standard deviation turns out to be the square root of NPQ, which should look familiar, I hope, from our sampling distribution problems, because this is just basically a proportion, right? So the standard deviation is square root of NPQ. It also turns out that the shape needs some help to be normal. So what we're going to do is use the normal approximation to help with this. But NP and NQ must both be greater than or equal to 10 to make this roughly normal and okay to do. So what that means is then you can answer a question like this. Sorry, this is just be putting it all together again. So just putting it all together. Normal approximate, what we're going to do is use a normal curve to approximate this. So if I ask a question like, what's the probability of at least 40 out of 70? Remember, I'd have this list that went 0, 1, 2, all the way to 70, and then I have to add up a certain amount. It'd just be way too many, right? So we're going to actually use this fact right here, that if NP and NQ are both greater than a 10, then it's going to be roughly normal. So N is the number of trials, P is the probability of success, Q is the probability of failure. If it's roughly normal, the mean will be NP, and the standard deviation will be square root of NPQ, and then I can use that fact rather than going back through and having to add up all these ones. We have to do this thing that's called a correction for continuity, which I'll explain in just a second. Okay, so I'll come back to that. It says go half a unit to the left or half a unit to the right. You'll see what that means in just a second. So here's the example problem. 37% of people fly on the 4th of July, probably a little bit different this year. We got to randomly pick 150 people. What's the probability that we get between 40 and 45? Now we could do this, right? We could add up. We could figure out the probability of getting 40 and 41 and 42 and 43 and 44 and 45 and just add them all up. We could do that. But we're going to use the normal curve to do it. All right. So first things first, the only time you ever do this approximation is if someone tells you. Do not do this on your own because it's going to give you a little different answer. We could add up. If I just ask this question in green, 37% of people find 45, randomly select 150. What's the probability to get between 44? You would need to do we would pick, I'll just do one of them, right? So we're going to go 150, choose 40, 40 successes, which means out of 150, 110 failures, right? And we would just do this for all of them, for 40, 41, 42, 43, 44. So someone just asked you that question. That's the way you have to do it. But if you want to use a normal approximation, don't unless someone tells you. So here's how we're going to do it. We're going to first verify it's binomial, make sure we can do all the things, make sure we can use the normal. Our NP and NQ greater than or equal to 10. These are both big numbers. So I think we're okay. I'll show you real quick. 0.37 is the smaller one, right? Times 150. 0.37 times 150 is 55.5. So the other one is going to be 94.5 for the other one. So we can use it. So we're going to find the mean and the standard deviation. We're just going to draw a little picture here, just like we've done before. So the mean, remember, is n times p. In this case, my n is that 0.37, or the 150, and the p is the 0.37. So it's the 55.5 that we just got. And the standard deviation is the square root of 150 times 0.37 times 0.73. All right, so now what we want to do is figure out what's the probability. It's between 40 and 45, including 40 and 45, right? So 40 to 45. So here's the continuity correction. The continuity correction, remember back here I said go a half a unit to the left or the right. It turns out that if I just hit right now normal CDF from 40 to 45, with a mean of 55.5 and that standard deviation, I can just do this on my calculator now. It's going to give me an answer, but the normal CDF, it turns out, does not count the 40 and the 45. Okay, it does not count the 40 and the 45. It counts between them. So we need to do what's called a continuity correction, and this is what you see me doing down here, is we just need to go half a unit. Seems a little bit weird. Why don't we just bump over a little bit to include the 40 and the 45? We could, but then some people might go over 0.1, 0.01, 0.01. So we just want everyone to stay consistent right now. And there is some pretty powerful math behind this that says our approximation is pretty good. So I'm just going to go over to the left, half a unit. It's going to put me at 39.5. I'm going to go over to the right, half a unit, going to put me at 45.5. Sometimes we only go in one direction depending on what they're asking. Just use the continuity correction if you have to. So we're going to go 39.5 to 45.5 with a mean of 55.5 and a standard deviation of point 150 times 0.37 times 0.73. Almost done. We're going to do a normal CDF from 39.5 to 45.5 with a mean of 55.5 and a standard deviation of square root of 150 times 0.37 times 0.73. And I get like 5.2%. So that's the normal approximation. Either only do that when they tell you, otherwise you just got to go step by step and add them all up yourself. But we'll never make you add up more than 3 or 4. Don't worry about that.